Hello and welcome. In this video, we're going to take a look at transformations of graphs. Now we're going to be looking at functions, basically, functions y equals f of x, and then take that and we'll see what we can do with it. Let's see if we can just add a value or subtract a value here or there, or scale it and see how that affects the overall shape of the graph. Now this is basically used assuming that we already know the shape of common functions, like a parabola, for instance. And once we have a basic graph and we know the basic shape, then it just takes a few manipulations to come up with the graph of a transformation of that. So let's say that you've got a function y equals f of x. It's a graph you already know. And we're going to just see by shifting or scaling something, what happens. Let's take this graph, for instance, y equals f of x. Not a well-known shape or anything like that, but let's suppose that we just know that the shape of y equals f of x looks like this. All right, well, let's start by doing a really basic operation like adding a constant. Let's suppose c is some constant, it's greater than 0. Well, what's going to happen if we just add c? Depends on where we do that to the notation. If we write y equals f of x, and then we add c, that's taking the result of f of x, which are the y coordinates of this red graph. And then we're going to add c onto the result. And that means that we're going to be shifting all of the coordinates up by c. This is a vertical shift upwards. Now, if we subtract c, now remember c is a positive number, so we're subtracting a positive number, then this is going to take f of x, which are the y coordinates of the red graph, and it's going to shift them down by c units. Okay, so here is this graph again. Now, if we take this graph, and let's suppose that we wanted to change it to f of x plus 1, then we're going to take the entire graph here and every point on it, and we're going to be shifting it up by 1 unit. So it has exactly the same shape, it's just been shifted upwards. If we wanted to have this be f of x minus 2, then we would take this graph and take every point on it and shift it 2 units downwards. But it doesn't change the shape. So this is known as a vertical shift. All right, well, a horizontal shift is similar. Now, once again, we're just going to be adding or subtracting a positive constant. But what happens if we add or subtract that to x, which is the input being put into the function f? That is going to be a little bit backwards, unfortunately. So you can see here we've got a coordinate on this graph at the point 2, 0. So when x is equal to 2, we can see that f of 2 equals 0. Now, what if I were to change this function and I wanted to make this y equals f of x plus 1? What would that do? Well, I know that if x is equal to 1, then I would have f of 1 plus 1, which is f of 2, which means I'd get 0 because it's the same function as before, it's still f. And that means that now I have a coordinate at x equals 1 with a y value of 0. And so that is going to take the existing graph that we know the shape of, and the new graph is going to actually have a point 1, 0. It's a little surprising. Y equals f of x plus 1 shifts everything to the left by 1, because if you plug those values of x in and add 1 to them, you should get the same y values as the original graph had. So that means that y equals f of x plus a constant c, a positive constant, is actually a shift left. And similarly, if we have f of x minus a positive constant c, well, let's think about what that would do to the original graph. Let's reverse this. Here is our original graph again, and you can see that we have the coordinate 2, 0 as an example. Well, what if we were to change this to f of x minus 2? Well, now as a result, suppose that we had x equals 4. Then at x equals 4, y is going to equal f of 4 minus 2, which is equal to f of 2. And we know from the original function that that equals 0. So we've got x equals 4, y equals 0. And that's going to transform all of the points the same way, taking the point 2, 0 and moving it 2 units to the right. You can see that y equals f of x minus a positive constant is a horizontal shift right. Okay, well, we've taken a look at what happens when we add a positive constant. What happens when we start multiplying All right, once again, let's suppose that c is still some sort of positive constant. What is going to happen when we take f of x and multiply by c? Well, remember x is our input. That's along the horizontal axis here. And we are going to take that x value, plug it into the function f, and get our output. And that's the y coordinate. But we've taken f of x and multiplied it by c. That's going to take every point and take only its y coordinate and scale it. And that can go one of two ways. So here you can see a point on the x-axis. It has a y coordinate of 0. Multiplying that y coordinate by anything isn't going to affect its location. And here I've got a point, let's say, at 3, 2. Now, if I were to multiply this function, let's say by 2, then that is going to double that y coordinate. Let's see what the graph of y equals 2 times f of x will look like. What this is going to do is it's going to take that coordinate, and since it's stretching it by 2, it stretches away from the x-axis. Points below the x-axis will be negative, and they're going to get stretched by a positive constant, and they'll get stretched away double the distance. So everything gets stretched away. And now, instead of the point 3, 2, we now have the point 3, 4. And instead of our original coordinate that was at 0, -2, we have a coordinate here at 0, -4. So that is taking a positive constant. This was a constant that was larger than 1. What happens if we were to maybe multiply by a small constant between 0 and 1? Well, that would have the opposite effect. Let's see for a value between 0 and 1. We'll move this graph off to the side and take a look at the original graph again. Here's the original graph, and you can see it's not been stretched yet. This time, I'm going to take the function and see what happens when I divide by 2, or simply multiply by a half. So I'm multiplying by a constant, it's positive, but it's between 0 and 1. What is that going to do? Well, you can use a couple points for examples again. 2, 0, you take its y coordinate and multiply by a half, won't change. So that is going to be a stationary point. But if we take the coordinate 3, 2, its y coordinate is going to be shrunk down to 1. It's going to be exactly half. And the coordinate here, 0, -2, that is also going to be halved, and it will be shrunk down. So it's not a stretch, it's a compression towards the x-axis. As a result, stretch this, and we'll stretch here. So same basic shape, but now it's been compressed, and it passes through the point 0, -1, and 3, 1. Now what happens if we multiply the input x by a constant? Well, we can see that this is all vertical stretch or vertical compression. And since multiplying f of x by a constant is a vertical stretch, we can imagine that multiplying x by a constant is probably going to be horizontal. But it may not be totally predictable as to whether we get a stretch or a compression. So let's try it out. Let's see what happens if we take our function y equals f of x and try out y equals, well, I don't know, 2x and see what happens. Okay, well, we'll have to remember kind of a similar method to looking at the horizontal shifts. Now, we did have the point original here. We can use this as an example. This coordinate would be at 3, 2. Well, now in the function y equals f of 2x, y equals f of, let's say, 2 times 1.5 for x is now going to be f of 3, and that is going to equal 2. So when x is equal to 1.5, we're now going to get the y coordinate 2. So this point is going to get shrunk inwards to an x value of 1.5 now. And this point on the original graph down here, this would be the coordinates at 0, -2. All right, well, if we let x equal 0, y equals f of 2 times 0 is going to equal f of 0, which is going to stay -2. What about this point over here at the coordinates -3, 2? Well, if we let x equal -1.5, then y is going to equal now f of 2 times -1.5, which is f of -3, which is equal to 2 from the original function f. And so this point is now going to move from an x coordinate of -3 to an x-coordinate of negative 1.5. And so what we end up with is actually a horizontal compression. Everything is going to be now half the distance from the y-axis. And so we will shrink this point in, and we will shrink both sides equally so that we still see that points that are on the y-axis remain on the y-axis. This is now the point 0, negative 2. We've got the point 1.5, comma 2, and we've got the point negative 1.5, comma 2. Now, what about if we have c being between 0 and 1? Well, here is our original function, y equals f of x. And now let's manipulate that a little bit. What if we were to change this to y equals f of 1/2 x? Well, that just means that from the original graph here, if we want to have the same y-coordinate as any of these points, the new x-coordinate needs to be twice as large. So if we take an x value that is twice as large, it gets multiplied by 1/2 before even getting plugged into the function f. And then it'll give us the same output as the original y values. And so this point here at 3, 2 is going to be stretched all the way out to 6, 2. The new graph is going to be horizontally stretched away from the y-axis. Now you can see we have the same basic shape, but it's definitely much more stretched out. So for c between 0 and 1, f of cx is a horizontal stretch. Now, last but not least, we can take a look and see what happens when we have the same scenario, but c is negative. Well, we can really just take a look and see what happens if we just slap a negative sign in front. All right, let's take a look at y equals negative f of x versus y equals f of negative x. Well, the negative sign in front of the function is simply going to affect the output. So when we plug in x into the function f, and we know what the normal value of f of x is, we simply need to negate that. And that becomes our y values being flipped from a positive y to a negative y, or from a negative y to a positive y. Anything that is below the x-axis is a negative y value. But in the function y equals negative f of x, it will become a positive y value. And anything that's a positive y value, in the function y equals negative f of x, it's going to be negated and become negative. So we take this particular function, and when we look at y equals negative f of x, we simply need to flip. And as a result, you see that the points here at negative 1, 0 and at 2, 0 will remain on the x-axis. They won't go anywhere because they have a y-coordinate of 0, which is neither positive nor negative, and the negation of 0 is still 0. Well, what about y equals f of negative x? That is going to be impacting what happens from the input before plugging into the function f. And so, if we have a coordinate that we know already, such as 2, 0, if we are going to be looking at the function y equals f of negative x, then our value of x will have to be negative 2 before plugging in to this f of negative x in order to get the same y value of 0. When x is equal to negative 2, then y is going to equal f of negative 2, which is f of 2, which should still equal 0 because we're still talking about the same function f. So now we're going to get the point back here, negative 2, 0, instead of the original point, positive 2, 0. As such, it happens with all of the points that we can just take the x-coordinate and negate them, and that turns into a flip. This time we are looking at a flip horizontally over the y-axis. You can see here that point negative 2, 0, and we also now have a positive 1, 0 instead of the original negative 1, 0. And points on the y-axis won't go anywhere. At 0, negative 2, well, the x-coordinate is neither positive nor negative, and the negation of 0 is 0. We have a vertical flip over the x-axis, and we have a horizontal flip over the y-axis. You can get some interesting behavior of certain functions, where if you flip it over the y-axis or x-axis, If you end up with exactly the same function as you had originally, we call that some form of symmetry. And there are two major forms of symmetry that we really need to know about functions that are going to be helpful for graphing them and helpful for some calculus that we might be looking at performing on those functions later. And that's even and odd symmetry. Even symmetry occurs when f of negative x is equal to f of positive x. So this would be if we take a function and apply the transformation of a flip over the y-axis horizontally. If it appears the same as the original function, that is even symmetry, and we say f is an even function. Odd symmetry, if we apply a flip over the y-axis horizontally, and we go back to the original function, but apply a flip vertically over the x-axis, if we see that either of those transformations produces the same graph, then we say that f is an odd function. For an example of even symmetry, we could take the parabola here, which has its vertex right on the y-axis. Now, if we were to take this function y equals f of x, and we looked at the transformation y equals negative f of x, we should end up with the exact same graph. Now, what would an example of odd symmetry look like? Well, we would need a function that, if we look at it backwards, it would be the same as looking at upside down, essentially. Anything in the top right quadrant, quadrant 1, if we reflect it across the y-axis, will end up in the top left quadrant, or quadrant 2. If we want an odd function, we would need something in quadrant 3, the bottom left corner, so that it can be reflected across the x-axis and also end up in quadrant 3. So any point over here is going to be reflected. We will need an equivalent point here to be reflected for odd symmetry. And so we end up with this interesting symmetry right through the origin. These 2 points should be equally far from each other through the origin. We call this kind of symmetry, symmetry across the origin. And here would be an example of a function that might look like that. So it has exactly the same shape going into quadrant 1 as it does going into quadrant 3, and every point on this graph is going to be perfectly symmetrical through the origin corresponding to another point at equal distance in the opposite quadrant. And this would be an example of perhaps a cubic function. Now, if we know that a function has even or odd symmetry, it just makes it very easy to plot. We only have to look at half the graph, and then we can imagine folding the paper and having symmetry for even, or we can take every point and mirror it through the origin to find the other half of the graph for odd symmetry. Well, transformations of graphs aren't something that we necessarily need to do ourselves very often. It is really so that if we have a very common expression, something squared, like x squared, it's going to have a common shape, and then we can just move it around and know what the new graph is going to look like. Anyway, that's it for this video. Thanks for watching. I'll see you again in the next video.